Hello and welcome again to my Physics Online video lecture series. In today's video we're going to be revisiting the Maxwell distribution, or if you prefer the Maxwell-Boltzmann distribution of molecular speeds to give it its longer name. And we're going to be looking at some kind of points of interest, if you will, within that distribution, namely the most probable speed, which is kind of the equivalent of a mode for a statistical distribution. It's kind of an analog to the mode value. We'll be looking at the mean value of the speeds, and we'll also be looking at the root mean squared value of the speed distribution, which is sort of the more appropriate value, or the value that I guess you could say ties more directly to energy, which is what this distribution is kind of derived from to begin with. So to get us started on this, we may need to recall a few things from the previous video. The main thing to recall is the Maxwell and Boltzmann distribution. So Maxwell-Boltzmann distribution is basically a probabilities distribution for particle speeds. I wrote it in that previous video using f of v as my probability density function. So this was 4 pi times n times the mass divided by 2 pi times Boltzmann's constant times temperature, quantity to the 3/2 power, times the speed squared times the exponential value of basically negative 1/2 m v squared average divided by k sub b times t. Now this comes from what is sometimes called the Boltzmann distribution. It's sort of an energy function. The Boltzmann distribution, for what it's worth, is also a probability density distribution, but it basically ends up looking more like this. I'm going to use lowercase n. It's a function of energy rather than a function of speed. It has some amplitude, we'll call that n naught, e to the negative of energy divided by this k sub b times t, this Boltzmann's constant times temperature factor. So note that, again, this term in the numerator of the exponent right here, this is kinetic energy, K. So kinetic energy on average. So in some sense you can see where this and this, where these two things are kind of linked to each other. We just have some additional factors out front that kind of play into this n naught term. And of course this is a distribution in terms of speeds, and this is a distribution in terms of energies. So they're not the same distribution, but in some sense this one is statistically determined or observed, and then the above one is now derivable from this. The other thing to maybe recall in all this is what the actual Maxwell-Boltzmann distribution looks like. And I'll just kind of plot one of these Maxwell distributions from the previous video. This, for what it's worth, is using something like room temperature, 293.15 Kelvin as our temperature value. I'm not going to plot the Boltzmann distribution in this video. It's interesting, but it's not maybe the important point in this video, because what we really want to be focusing on is some speeds that come out of this Maxwell distribution. So in fact, I'm going to actually paste this distribution, but maybe a little bit larger, so that I can highlight some points in it. There's really kind of three speeds, if you will, that we might be interested in. one of them is this peak value. So this peak tells us what is called most probable speed. And it's worth noting, this often is, by the way, VMP for most probable. It's worth noting, again, that this exact speed, there isn't necessarily any molecule that has it, but if you wanted to figure out how many molecules have very nearly this speed, then this is sort of the choice that you're going to get the largest number of molecules that have this exact speed. So in other words, this frequency of occurrence among molecules in some sense is a misnomer, in as much as like no individual molecule has an exact speed of, let's say, 498.000 repeating meters per second. They might be 498.1 or 498.0, like those are attainable. But notice that if I have 498. Let's say 095, I would just round that to 498.1. Okay, and so there's basically like a bin of values in here. And that actually is maybe fodder for a different video example. So this is the most probable speed value. How do you obtain that value? Well, I'd like to actually do that maybe in a separate video. In this one, I'm just going to state the value. And so the most probable speed, V most probable, given the distribution that I've given to you, is actually given by square root of 2 kBt, so 2 times the Boltzmann's constant times the temperature, divided by the molecular mass. Okay, so in some sense you're just taking an energy value, a kinetic energy value, and dividing it by kBt and then solving the whole thing for V probable. Okay, so that's your most probable speed. There's actually 2 other speeds of interest, and they're a little bit harder to label on this graph, but they typically have larger values than the one that I've just sort of grabbed for you. Okay, there's the average speed. So the average speed actually is going to be somewhere over here. As it turns out, it typically is larger than the peak. And I'm just going to write that over here, V average, and that is going to be given, as it turns out, by square root of 8 kb times T divided by pi times the molecular mass. And note that over here I have 2, over here I have 8 over pi in the square root. So 8 over pi is greater than 2. So this average speed is actually greater than the most probable speed. Okay, and then last but not least, I have what's called the root mean squared value. So VRMS, that stands for root mean squared. And by definition, that's just the square root of the average of the square speeds. So that in turn is, as it turns out, given by square root of, and then what we have on top here is 3 k sub b t over m. Okay, so in some sense these right here are your equations for figuring out your speeds. And you know, if I were to sort of label them on here, maybe in colors, I'm going to kind of label this guy in green. This is typically going to be somewhere in here. Okay, so in some sense this right here might represent my average speed, and then if I wanted to get my RMS value speed, that's typically going to be higher still. Okay, so you have to kind of drop these dashed lines down to wherever they happen to hit on the axis. So I've got my most probable speed, that's actually the lowest speed. Then I have my average speed, which is the next lowest. I have my RMS speed, which is sort of the greatest of these. So we can write that V RMS is greater than V average is greater than V most probable. Now, in a previous video, I kind of introduced these ideas, and I did a quick example that illustrated the difference between an average and an average square. So you might want to go back to that video to sort of look at where this number versus this number comes from, and that was discussed in this Maxwell distribution of speeds video. So let's take this short example. Let's say that we have 3/4 of a mole of helium gas at room temperature. So 0.750 moles of this helium. And it's at room temperature. And what we're wanting to get is basically these three speed values. Most probable speed, average speed, and RMS speed for these helium molecules. Okay, so in order to solve this, we first need to note that room temperature is 20 degrees C, but that is basically 293.15 Kelvin. Okay, so we're given a temperature. And second, we need to know what helium implies. Okay, so helium, the mass of a helium, we typically have four kind of components to it. So there's usually 2 protons and 2 neutrons. Now, we haven't really discussed protons and neutrons at this point in physics, but in some sense you can approximate this as being 4 times the mass of a hydrogen atom. And a hydrogen atom is approximately 1.67 times 10 to the negative 27 kilograms. So that's how you're going to get the mass for these guys. All right, so that's about 6.68 times 10 to the negative 27 kilograms. Also worth kind of recalling, and this is maybe going back up here to the equations that we've written, is what is the value of the Boltzmann constant? So Kb is the Boltzmann's constant again, and that is about 1.38 times 10 to the negative 23 joules per Kelvin. So again, fundamental constant means value doesn't change from one application to the next. Okay, so basically we should be able to just plug this mass and this temperature and etc. into our distribution. Why does this 0.75 moles part really matter? It doesn't. It doesn't really matter that much as to why we've chosen this. The answer doesn't change. In other words, if I choose 0.5 or 3 or whatever, we just needed a large number of helium atoms. And so 0.75 moles is a large number. It's 0.75 times Avogadro's number. So in other words, we don't really care how many moles worth of the sample there are. We just care that there's a large enough number that these Maxwellian distribution can apply. So 0.1 mole, 0.01 mole, 0.001 mole, those are all still a large number of molecules. So all right, with that little caveat aside, this is kind of therefore like what you might call quasi extra information. You need to know it in as much as you needed to know that there's enough to make these equations valid, and after that we can discard it. So what are the speeds in question? So let's start with the most probable speed. So V most probable is given by square root of 2 times kb times t divided by mass. So we're looking at square root of 2 times 1.38 times 10 to the negative 23 joules per Kelvin times 293.15 Kelvin divided by the mass that we found up here, 6.68 times 10 to the negative 27 kilograms. All right, so that's what all you'd be plugging into your calculator. What does that give us? We obtain a speed of 1100 meters per second. Now, before I go any further with this, you may be thinking back to the graph that I showed you and saying, now wait a minute, 1100 meters per second is like way over here. This peak clearly is not at 1100 meters per second. Okay, if you were that perceptive, great. So I probably owe you another plot. The reason being that this plot and this distribution does factor the mass in. And when I made this plot originally, you can see the mass, 5.31 times 10 to the negative 26. That is fairly close to the value that you'd expect for one of these molecules, not for helium. Therefore, if I make a couple little changes to my code to actually be plotting for a helium atom, and yeah, I made a couple changes. I decided to just put the mass in terms of hydrogen atom masses. So helium would be 4 of those. So my new mass is 4 times this hydrogen atom mass. And then I go and replot. Sure enough, if you look, you can see that the peak is now somewhere past 1,000 meters per second. We can even estimate it if we want to be really clever here and add some more features to our code. We could estimate it by sort of adding the grid to it. So if I come down here and just ask it to put a grid on, so grid on, then this replot gives us a nice little grid. Here's 1,000 on this vertical line. Here is 1,500. This looks like it could be a good fifth of a way between these two. So 1,100 is suddenly a very credible answer for our most probable So, you know, here is for something that has more like the mass of an actual helium atom. So this is helium molecule, or helium atom as it turns out, at room temperature. So again, this is a much more reasonable value than it would have looked if you just looked at the original plot. All right, so now let's keep going. Let's calculate our other two speeds, our RMS speed and our average speed. So V average. Recall that the average speed is what you would get if you just took all of the molecules' speeds, added them all up, and then divided by the number of molecules. And again, I've kind of shown a example of what that looks like in my previous video. So this right here basically looks like the square root of 8 over pi times kb t over m. And so let's plug those numbers in, and what we get is roughly 1,241.84. So let's take this to maybe 3 digits of precision, so 1,240 meters per second. All right, so that's our average speed, and that is in fact greater than our most probable speed. Last but not least, we might want to get the RMS value, the root mean squared value of speed. Again, this is akin to taking all of the molecules' speeds, squaring the values, adding them all together, and then dividing by the number of molecules that you've added, and then taking that final answer and taking a square root of it. So from the Maxwell distribution, that ends up being equal to basically 3 times kBT over m. And so if you plug numbers into that, what you get is about 1,347, or again, rounding to 3 significant figures, about 1,350 meters per second, which again is greater than the average speed, which was greater than the most probable speed. All right, so this video is already a little bit in the overlong category, so we will stop with that example for today. Hopefully you found it helpful, and also I hope that you kind of enjoyed the little diversion into replotting this distribution of molecular speeds to account for helium rather than whatever molecule I had plotted it for before. I think I maybe had it for oxygen, but I forget. I guess you could go back and rewind the video and see what massive molecule I had. It may be something smaller than oxygen. But in any case, hopefully you found that fun as well. And hopefully this example was helpful. So until the next one, thanks for watching.